today we're going to apply some of the logic that we've learned so far so that we can broaden the connections that we can make and broaden our vocabulary along the way. So far we've had symbols of negation, of disjunction, of conjunction, of implication, and the biconditional. All of these are called logical connectives of one form or another. So when we take these connectives and we put them together, we can make statements that are more complicated. So there's an example of a statement there that we have P or Q and P or R. So we're using three statements, P, Q, and R, and we're using the connectives of a disjunction and a conjunction to put all of these things together into a more complicated logical statement. So statements like this are called compound statements. They're composed of one or more statements. So we only necessarily need one logical statement, but we can use more. And they have at least one logical connective. All of the statements that go into this are called component statements. So an example with just a single statement is down below. We have P or not P. Well, we said P has to be true or false, not P has the opposite value. So that's always true, that statement. And statements like that are always true no matter what the value of the component statements is, so what the value of P is, are called a tautology. So again, whether P is true or false, that statement is true. And whenever we have all of the component statements can be any combination of true and false, and we put them all together into our compound statements, and the compound statement is true always, then it's a tautology. So here's an example of a tautology. We have the statement not Q or P implies Q. So one of the ways that when you're trying to figure out if something's a tautology that you can go about it is to check a truth table. And honestly, that's probably going to be your easiest way to go about it, pretty much always. So here we have P and Q. We need to get all of the possible truth values for them. And we go through and we make a column for not Q. Again, just flipping the truth values of Q. We make a truth value column for P implies Q, following our implication rules where it's only false when Q is false and P is true. And then where we've used our P and Q columns, and now we're using our not Q and our P implies Q columns that we've created to combine them and follow the rules of our disjunction. So remember, a disjunction is true whenever at least one of the statements is true. So in this case, this first row, I have P implies Q is true, so the disjunction is true. When I have not Q is true here, then it's true. I have P implies Q is true here, so it's true, and they're both true, so it is true. So whenever we get a column that is all true, then that statement is a tautology. Polar opposite of tautologies are contradictions. So in this statement, no matter what the truth value of all of those component statements are, then the outcome is a contradiction. So an example of that is P and not P. It's not possible for both of those to be true at the same time, and so that statement is always false. So a bigger example of that, if we have P and Q, and P implies not P, then we can go through and we can build up our logic table. Again, this is a great way to figure out contradictions the same way it is tautologies. So we take all of our possible truth values for P and Q, all the combinations, and we get our 4 rows. And we go through and we see what component parts we're going to need. So we're going to need a not P, so we make a column for not P. And we just flip the truth values of P to make that column. And then we're going to need a P and Q column. So I make a P and Q column, and P and Q is only true when both P and Q are true. So I check P and Q are both true here, so it's true. And every other time, one of them at least is false. So P and Q will be false for the rest of those. Then I'm going to need a P implies not P. So I've got, a Q implies not P column. So I already have a Q column and I have a not P column, so I'm ready to make that implication column. So in this statement, implications, remember, implications are always true unless Q is true and not P is false. So I go through, Q is true, not P is false, so it's false. And then every other time, either Q is false or not P is true. And so I have a column that looks like that. And now I have the component parts, the right-hand side and the left-hand side, all put together, and I can take that conjunction. So remember, the conjunction, to be true, both statements must be true. So I go through, and in every single row, at least one of the statements is false, and so I get an entire table of false values for that conjunction. And that means that the statement is a contradiction. So we're going to see that the two examples we've done of the more complicated tautology and its negation, the contradiction, were actually negations of the same statement. So to be able to look at that, we need to think about logical equivalence a little bit. So when we have compound statements, a pair of compound statements that have the same component statements involved in them. So if statement R has component statements A, B, and C, then compound statement S also has to have component statements A, B, and C involved. All right. So they're called logically equivalent. We say the compound statements are logically equivalent if the truth values of all the combinations of truth values for the component statements result in the same truth values for R and S. So basically we're looking for two columns of a truth table where the two columns match identically the whole way through. All right, so if they're logically equivalent, then we write this as one of the statements and then a trio of horizontal lines in between, like an equal sign with one more, and then we write the other statement. And we read this, R is equivalent to S. So here's an example worked out with the truth table. So P implies Q. It's actually logically equivalent to not P or Q, and we're going to show that that's true. So again, we make our truth table. We have P and Q, all the possible values. We're going to need a not P column. So there's my not P column, flipping the truth values of P every time. And then I'm going to need a P implies Q column. So P implies Q column, only false when P is true, Q is false. And then I'm going to need a not P or Q column. So the other side of this equivalence. And again, here I have a disjunction, and disjunctions are only false when both statements are false. So only looking for when not P and Q are both false, which happens in the second row here. Otherwise, it's true because at least one of the statements is true. So notice the two columns here match identically, and that makes the two statements logically equivalent. So this logical equivalence that we saw is a super important one, and we're going to be coming back to it multiple times throughout the course. So just kind of file it away in the back of your head. It's going to be incredibly useful to you. And we've actually already used this logical equivalence in an example that we did back at the very beginning of chapter 2. So there's a bunch of laws of equivalence, of logical equivalence that we'll be using throughout the semester. Most of these are pretty intuitive. Some of them take a little bit to really think about. So honestly, if I were you, I would be filing away this theorem somewhere, like possibly printing this out. I would possibly be like taking the theorem in the book and like highlighting it somewhere, like slapping it on a wall beside where I'm going to do my homework, because these things will be super helpful to you along the way. So again, instead of me reading through all of them, I'm going to say, here they are. We're going to use them. All right. De Morgan's laws are probably the most strange to grab a hold of. So De Morgan's laws are taking the negation of disjunctions and conjunctions and pulling them apart so that the negations are on either side of the disjunction and conjunctions. And when you do that, you have to flip whether it's a conjunction or disjunction. So we had a disjunction, and then when we took the negation to both sides, it became a conjunction, and vice versa. So we're going to take a look at De Morgan's laws being used now. So we're going to do an example where we're trying to show that actually back when we were talking about tautologies and contradictions, the examples that we were using there, we're going to show that we had some logical equivalence that was helping us have those two examples. All right, so if we have not P implies Q is equivalent to P and not Q. So we're trying to show this equivalence. So whenever we're trying to show equivalence, we can either go through and make a logic table, or we can go through a series of logical steps using those laws that were in the previous theorem along the way, so that we can show that two things, we can start one place and end up at the other place. So the truth table is great to check your gut. It's a great start. But we're going to go more and more towards this type of argument because this is our stepping stone towards doing proofs. All right, so we can start with not P implies Q. And if we take our equivalence that we had earlier, that first theorem that I said we were going to use a lot, that we were going to tuck away, that tells us that P implies Q is equivalent to not P or Q. So I just can replace my implication here with not P or Q. See, this logical equivalence helping us out already. So now I've got not P or Q. And then notice I have a not on the outside and a disjunction on the inside. So it's hard to work with this stuff the way it is, and it's really messy looking. So whenever something's super messy looking and you have a not on the outside, sometimes Morgan's laws, it's worth a shot applying one of them. So that's what we're going to do. So De Morgan's law says, hey, put the not with the things on either side and change disjunctions into conjunctions. So we've put a not with the not P, and we've put a not with the Q, and we've changed our disjunction into a conjunction. All right, so De Morgan's law is the reason this equivalence right here works. And in the example, they don't give the reason above or below the equivalent sign. It's a really good habit when you've made a jump like this to just write here, De Morgan's law. All right, then you know why you did it the way you did. And if you run into a problem, you can double check that you used De Morgan's law properly. It's very common for people to forget a negation or to forget to flip the disjunction conjunction. So once we've done this though, we've done it properly, then we have not P. Well, we know by our definition of negation that this is the equivalent to P, and we have not Q over there. So P and not Q, and lo and behold, we are exactly where we wanted to be. So now we have a string of logical equivalences that I can actually omit all of the middle work now, that application of De Morgan's law, and I can say, well, then the statements not P implies Q and P and not Q are logically equivalent. And we used that actually in our examples of tautology and contradiction earlier. So we used De Morgan's law And this is what this is saying. Hey, we used De Morgan's law. This is what we did in that last example. We showed that not P implies Q is equivalent to P implies not Q. So taking what we did and looking at it and changing our implication into a biconditional, it changes some, but we can actually follow similar logic. So if we have not and a biconditional between P and Q, this is equivalent to not P implies Q and Q implies P. So this is just the very definition of the biconditional, right? We have the original implication and its converse both in there. Now we can apply De Morgan's law, and we can put a not with both of these implications and change our conjunction here into a disjunction. So I have not P implies Q or not Q implies P. Now both of these look like exactly what we did before, so I actually know that not P implies Q is equivalent to P and not Q from the work that we did in the previous example. And similarly, not Q implies P is equivalent to Q and not P. So I have P and not Q or Q and not P. And that's logically equivalent to the negation of my biconditional. So this is just the two things that we worked out in the examples turned into a theorem. So I have the negation of the implication and the negation of the biconditional written in ways that we're going to be able to use to help us out as we move forward through the semester.